Okay, so this is the third review video for Calculus 1, Math 1560, and in this video we're going to talk about sets, and we're going to talk about interval notation, right? The most common sets encountered in calculus course are intervals, so we'll try to pay most of our attention there. I'm going to try to move quickly through this one because I'm trying to keep these videos short. The first two have been kind of in the 15-minute range, and I want to get these all under 10 minutes if I can. So let's keep moving. So what is a set? Well, it's hard to give actually a rock solid definition of a set in a very basic math course. There are all kinds of issues that you can get into if you're not really careful defining sets, but those are topics for a course that is not calculus. So the kind of hand-wavy definition you often see is it's a well-defined collection of objects. Well, okay, that's kind of cheating, right? Because we just use collection, which is a synonym for set, to define it. So we're talking in circles, but set that aside for a moment. What we really mean is you know, you've got a bunch of things, and there's some way to tell which things belong to your set and which things don't belong to your set, right? So if I say something like E is the set of even integers, well, that works because I know what an integer is and I know what it means for an integer to be even. I know that the even ones are the multiples of 2. So I can look at any number, right? I can first ask, is that thing an integer? Yes. Is it divisible by 2? Yes. Okay, it's in the set. If my answer out of those questions is no, well, then it's not in the set, right? And we go from there. Now, of course, there are various ways to describe sets. I think some of these will come up on the next slides, but just, you know, the way you've probably seen that you might write something like this out is this curly bracket notation for a set. So we might say, well, okay, there are infinitely many entries in the set, so I can't list all of them, but I can kind of give you the general pattern. -4 is in there, -2 is in there, 0 is in there, 2 is in there, 4 is in there. Right. And the ... on either side is your indication that you should follow the pattern in either direction and keep, you know, writing down the even integers as you go, the positive ones and the negative ones. Okay. So however you want to describe that set verbally, as a list, you could describe it as, you know, you could describe it using a formula. You could say things like it's the set of all numbers of the form 2 times k, where k is an integer. This capital Z is our notation for integers. We'll get to that in a second, right? There's lots of different ways that you could describe that set. Okay, and well, you know what? Let's speed things up. We just kind of covered it, right? Here's our verbal description. This is often called the roster notation. So this is verbal. This is the roster. This is an example, and we'll see many examples like this. This is what's called the sort of set builder notation, right? It tells you how to construct the set. It says, well, take all the, you know, start with the integers, multiply them by 2, you've got the set. All right, so those are the 3 ways of defining your set. Now, of course, sets are not restricted to just numbers. You could talk about, I don't know, sets of people, sets of cats, whatever you want to do. But you got to make sure that whatever kind of sets you're talking about, you have some way of deciding what belongs and what doesn't. Okay, so let's skip right ahead because we want to speed things up. Okay, so this element notation, I don't know if you guys, some people have probably seen it, some people haven't. This is the symbol that we use when we want to tell you that a particular object belongs to a particular set. So if I want to tell you, for example, so with E being our set of even numbers from the previous slide, let's say I want to tell you that 6 is an even number, I could tell you it by saying that. 6 is an element of the set E. 6 belongs to E. There are a number of ways you can write it. All of them tell you that 6 is an even number. Okay. If I want to say that something doesn't belong to the set, so for example 7 is not an even number, you do this classic, this slash. Any kind of math symbol, if you put a slash through there, that kind of adds a naught, right? So 7 is not an element of E. 7 is not even. Okay. So you'll see this kind of notation quite a bit. You'll see things like, well, one of the ones you'll see all the time is I want to tell you that x is a real number. So you see things like that. X is an element of R. Right? This means that x is a real number. Okay. So anytime you see this this kind of funny curly looking E, right, this is us trying to tell you that a particular number belongs to a particular set, right? We'll often use this for things like describing, let's say, solutions to equations or solutions to inequalities. We might want to write down the set of all solutions, and then I want to tell you that a particular number is a solution, and so I use this membership notation to tell you that it belongs to that set. Okay. Subset notation, probably not going to come up too much in the course, but I feel like I should mention it just for completeness. Okay, so the element notation that we used on the previous slide, this is a relationship between objects and sets, right? 6 is an object, E is a set containing that object. The subset relation is a relationship between two different sets, and this is the symbol that we use if we want to tell you that everything belonging to one set is also in another set. So, for example, if I wanted to tell you that, this set of even numbers is a subset of the integers, I can do that. Right? Every even number is in particular an integer. I could also say, well, you know what, and every integer is also a real number. So I could write something like that. So you'll see this subset notation occasionally, but infrequently. Okay? And that brings us to, well, more notation. Sorry, guys. I forgot what order my slides were in. Okay, special sets of numbers. N. What is N? N is a set of natural numbers. 1, 2, 3, 4, and so on. So these are the so-called natural numbers. Okay. Occasionally you might see people that tell you that 0 is also an element of the natural numbers. There's some, depending on kind of the context, some disciplines include 0, some don't. It's fine. You just have to make sure that you tell people whether or not 0 is in there. Usually in calculus we don't include 0. In other courses you might include 0. It's nothing to lose sleep over. The integers, these are, well, you take the natural numbers, you throw in all the negatives, and you also throw in 0 if it's not already there. So -3, -2, -1, 0's in there, 1, 2, 3. The rational numbers we've already seen. These are all your fractions, so this is the set of all things of the form P over Q, where P and Q are integers and Q is not equal to 0. Okay, and finally we have R, the set of all real numbers. So this includes the rational numbers plus all the irrational numbers, root 2, pi, all of those guys. We won't actually carefully define the real numbers in this course. It turns out if you want to actually give a proper definition of the real numbers, this is super hard. If you get to a course like, let's say, Math 3500, our third year analysis course, maybe you'll see a definition of the real numbers there. It's quite difficult to give a careful definition of the real numbers. Some of you might find that unsatisfying because the real numbers are kind of the building blocks for all of calculus. All the work we're going to do is really dependent on kind of this foundation of the real number system, and we're not even going to tell you how the real numbers are defined. It's one of those things that you're just going to have to wait on, unfortunately. Okay. One of the ways we kind of get around this is, well, we view the real numbers, you know, as this number line. So the integers are in there, the fractions are in there, your irrationals are in there. So square root of 2, for example, is probably somewhere around there, right? And so the real numbers, kind of the essence of the real number system is this notion of continuity, that there are no holes or gaps in that number line. It's this continuum, which is not something that you achieve with the rational numbers, even though there are many, many, many rational numbers, right? And you choose any two rational numbers, even two rational numbers that seem really close together, like a half and a third, and there are infinitely many rational numbers in there. They're packed in there really super tight, and yet somehow there are still gaps in the line, and you need to fill them in. You need to add these irrational numbers. And so this is why it is really hard to actually give a careful definition of the reals. Okay. Now, among real numbers, the most important subsets of the reals, the ones that we spend most of our time working with, are the intervals. Okay. And so it's important to be comfortable with interval notation because you're going to see it quite a bit. Closed interval. The interval from A to B. The square brackets indicate that you're including the endpoints. So this is the set of all real numbers x such that A is less than or equal to x and x is less than or equal to B. Right? So it's all the numbers between A and B including A and B. Okay? The open interval, you don't include the endpoints. So this is the set of all real numbers where x is strictly bigger than A and strictly less than B. And then we have these so-called half-open intervals. So as you might guess, this tells you that you should include the left endpoint but leave out the right endpoint. Okay? And similarly, this guy is going to be the set of all numbers strictly greater than A but less than or equal to B. And then there are various infinite intervals, ones involving infinity. So everything from A up to infinity, this is the set of all things bigger than or equal to A, right? So notice that each interval is basically a stand-in for some sort of inequality, right? X is bigger than or equal to A. If I use the round bracket, that means I'm leaving out A, so X is strictly greater than A, okay? And if I go off to minus infinity, that means I'm looking at values less than that value. So here x is less than or equal to b, and here x is strictly less than b. Okay, so those are all the standard intervals. You could also, you'll see kind of everything from minus infinity up to plus infinity. Well, that's a set of all the real numbers. One caution, of course, is that infinity itself, not a number. Infinity is not a number. Infinity is kind of a destination that you never reach. Okay, and so you never see a square bracket with infinity because there is no number infinity. This is just the indication that you keep going on forever in one direction or another, right? You can always find bigger and bigger and bigger and bigger and bigger numbers, and you never reach an end, and that's what infinity is telling you. Okay. The only other thing that you might see, and let's just mention this for completeness, you might be in situations where maybe you have to include everything from 1 up to 2, not including 2. We often use these kind of solid and hollow dots to indicate that. And then maybe you include the numbers bigger than 3 but less than or equal to 4, and you want to include everything in here, and you want to include everything in here. Now, because there's a gap, you can't write it as an interval. Intervals are always one solid piece. There's a gap in between. So how do you write something like this? You use what's called the union symbol, which is this big U, which tells you that you take everything that's either in the first interval or in the second one. So you'd write this as everything from 1 to 2, and then this big U, union, the things from 3 to 4. Okay, so that's one other set symbol that you'll probably have to use in this course.